2.2 The Planetary Model of the Atom. The stage was now set for the unexpected discovery that the positively charged part of the atom was a tiny, dense lump at the atom's center, rather than the cookie dough of the raisin cookie model. By 1909, Rutherford was an established professor and had students working under him. For a raw undergraduate named Marsden, he picked a research project he thought would be tedious but straightforward. It was already known that although alpha particles would be stopped completely by a sheet of paper, they could pass through a sufficiently thin metal foil. Marsden was to work with a gold foil, only 1,000 atoms thick. The foil was probably made by evaporating a little gold in a vacuum chamber so that a thin layer would be deposited on a glass microscope slide. The foil would then be lifted off the slide by submerging the slide in water. Rutherford had already determined in his previous experiments the speed of the alpha particles emitted by radium, a fantastic 1.5 times 10 to the 7 meters per second, if I read that right. The experimenters in Rutherford's group visualized them as very small, very fast cannonballs penetrating the cookie dough, part of the big gold atoms. A piece of paper has a thickness of 100,000 atoms or so, which would be sufficient to stop them completely, but crashing through 1,000 would only slow them a little and turn them slightly off their original paths. Marsden's supposedly ho-hum assignment was to use the apparatus shown in the figure to measure how often alpha particles were deflected at various angles. A tiny lump of radium in a box emitted alpha particles, and a thin beam was created by blocking all the alphas except those that happened to pass out through a tube. Typically deflected in the gold by only a small amount, they would reach a screen very much like the screen of a TV's picture tube, which would make a flash of light when it was hit. Here is the first example we have encountered of an experiment in which a beam of particles is detected one at a time. This was possible because each alpha particle carried so much kinetic energy they were moving at about the same speed as the electrons in the Thomson experiment, but had 10,000 times more mass. Marsden sat in a dark room watching the apparatus hour after hour and recording the number of flashes with the screen moved to various angles. The rates of the flashes was highest when he set the screen at an angle close to the line of the alpha's original path, but if he watched an area farther off to the side, he would also occasionally see an alpha that had been deflected through a larger angle. After seeing a few of these, he got the crazy idea of moving the screen to see if even larger angles ever occurred, perhaps even angles larger than 90 degrees. The crazy idea worked. A few alpha particles were deflected through angles of up to 180 degrees, and the routine experiment had become an epoch-making one. Rutherford said, "We have been able to get some of the alpha particles coming backwards. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Explanations were hard to come by in the raisin cookie model. What intense electrical forces could have caused some of the alpha particles moving at such astronomical speeds to change direction so drastically? Since each gold atom was electrically neutral, it would not exert much force on an alpha particle outside it. True, if the alpha particle was very near to our inside of a particular atom, then the forces would not necessarily cancel out perfectly. If the alpha particles happened to come very close to a particular electron, the mathematical form of the Coulomb force law would make for a very strong force. But Marsden and Rutherford knew that an alpha particle was 8,000 times more massive than an electron. and it is simply not possible for a more massive object to rebound backwards from a collision with a less massive object while conserving momentum and energy. It might be possible in principle for a particular alpha to follow a path that took it very close to one electron, and then very close to another electron, and so on, with the net result of a large deflection, but careful calculation showed that such multiple close encounters with electrons would be millions of times too rare to explain what was actually observed. At this point, Rutherford and Marsden dusted off an unpopular and neglected model of the atom, in which all the electrons orbited around a small, positively charged core or nucleus, just like the planets orbiting around the Sun. All the positive charge and nearly all the mass of the atom could be concentrated in the nucleus rather than spread throughout the atoms as in the raisin cookie model. The positively charged alpha particles would be repelled by the gold atom's nucleus, but most of the alphas would not come close enough to any nucleus to have their paths drastically altered. The few that did come close to the nucleus, however, could rebound backwards from a single such encounter, since the nucleus of a heavy gold atom would be 50 times more massive than an alpha particle. It turns out that it was not even too difficult to derive a formula giving the relative frequency of deflections through various angles, and this calculation agreed with the data well enough, to within 15%, considering the difficulty in getting good experimental statistics on the rare, very large angles. What had started out as a tedious exercise to get a student started in science had ended as a revolution in our understanding of nature. Indeed, the whole thing may sound a little too much like a moralistic fable of the scientific method, with overtones of the Horatio Alger genre. The skeptical reader may wonder why the planetary model was ignored so thoroughly until Marsden and Rutherford's discovery. Is science really more of a sociological enterprise in which certain ideas become accepted by the establishment and other equally plausible explanations are arbitrarily discarded? Some social scientists are currently ruffling a lot of scientists' feathers with critiques very much like this, but in this particular case, there were very sound reasons for rejecting the planetary model. As you'll learn in more detail later in this course, any charged particle that undergoes an acceleration dissipates energy in the form of light. In the planetary model, the electrons were orbiting the nucleus in circles or ellipses, which meant they were undergoing acceleration, just like the acceleration you feel in a car going around a curve. They should have dissipated energy as light, and eventually they should have lost all their energy. Atoms don't spontaneously collapse like that, which was why the raisin cookie model, with its stationary electrons, was originally preferred. There were other problems as well. In the planetary model, the one electron atom would have to be flat, which would be inconsistent with the success of molecular modeling with spherical balls representing hydrogen and atoms. These molecular models also seemed to work best if specific sizes were used for different atoms, but there is no obvious reason in the planetary model why the radius of an electron's orbit should be a fixed number. In view of the conclusive Marsden-Rutherford results, however, these became fresh puzzles in atomic physics, not reasons for disbelieving the planetary model. Some phenomena explained with the planetary model. The planetary model may not be the ultimate perfect model of the atom, but don't underestimate its power. It already allows us to visualize correctly a great many phenomena. As an example, let's consider the distinctions among nonmetals, metals that are magnetic and metals that are non-magnetic. As shown in the figures, a metal differs from a non-metal because its outermost electrons are free to wander rather than owing their allegiance to a particular atom. Oh, someone's at the door. I'm going to pause it. As an example, let's consider the distinctions among nonmetals, metals that are magnetic, and metals that are non-magnetic. As shown in the figures, a metal differs from a nonmetal because its outermost electrons are free to wander rather than owing their allegiance to a particular atom. A metal that can be magnetized is one that is willing to line up the rotation of some of its electrons so that their axes are parallel. Recall that magnetic forces are forces made by moving charges. We have not yet discussed the mathematics and geometry of magnetic forces, but it is easy to see how random orientations of the atoms in the non-magnetic substance would lead to cancellation of the forces. Even if the planetary model does not immediately answer such questions as why one element would be a metal and another a nonmetal, these ideas would be difficult or impossible to conceptualize in the raisin cookie model. Discussion question. In reality, charges of the same type repel one another and charges of different types are attracted. Suppose the rules were the other way around, giving repulsion between opposite charges and attraction between similar ones. What would the universe be like? That's pretty deep.